respect to x, right? Kids, hi. Shh. Doing the derivative with respect to x. So what do you end up with? Well, oh, it's e to x is in the power there, so this is just along for the ride right there. But then you have to, oh, I see what they did. So they did the derivative. Where does this come from right here? What is that? It's the chain rule from the power of e, right? This is just along for the ride, right? And then they just clean it up a little bit. Arbitrarily, they just clean it up. Great. Yay. Fun. Well, what about do you have a question about the mechanic or about how they cleaned it up? Which part do you have a question? This right here, this is the derivative with respect to x of what?
Power.
Of this thing right here, right? You differentiate that with respect to x and you get this right here. That's where it comes from. You kind of get that? Yeah. Yeah-ish? Okay. And all they do from here, there's no differentiation. They go from this side to this. Sorry, they go from this. They go from this side to this. That's just algebra to clean it up. That's all they did there. It's hard because you have to keep track of all the Greek letters, which are constants. All the Greek letters are constants. They are. Now, does that kind of make sense right there? What we did there? So they did. So going from side to side, it was this, and going up and down, it was right there. And it happened that they set up some nice contour lines that make it so that, I mean, do you remember when you did when you made linearizations with like scatter plots? You have a scatter plot of data, and then you draw your line of best fit, and then you find the equation. The rule for that is you want points that are generally farther apart if you can, but you want ones that you can estimate accurately. So you're always like looking for, like, as you keep on going out, which ones crosshairs, like which ones are actually measurable nicely. They set this up nicely for you. They're giving you more contour lines, right? Does everybody understand what they're giving you right there? Yeah. They're giving you more contour lines. So f of x with x equals 1.9, 2, 2.1, and y equals 0.9, 1, and 1.1. So how would you go about doing that?
Table values.
When you're estimating with f 1.92 and 2.1, the book likes to go forward. You could go from 1.9 to 2. You could also go from 1.9 to what? 2.1, right? So you could if you wanted to. What's another way you could have written this? What's another way you could, so this is the estimate, right? So what's another way you could estimate this, 2.21? You do f of 1.9, right? Comma. Actually, you know what? Let's do it and make it positive, shall we? So how about this? F of 2.1, comma, 1 minus f of 1.9, comma, 1 all over what? 0.2. It goes 0.2. This is what I would do right there. That's the one I would choose. This is my personal background. Does everybody kind of see what this right here? This right here also mirrors what we did right here, right? We did the points around it, so you could always do it around it. Do you guys want decimal answers for these? Just to give you.
I think it's numerical. No decimal.
It's a calculator. So I mean, they went forward. Great. They just went forward. Okay, so they get just approximately, so for f of x 1, they get approximately 4.1. And when they do fy, can you see that? Is that gray showing up at all? Yeah. It's not bad. 2.1. Great. Wonderful. So then C was the one I think people were also asking about.
Because I didn't see it.
Yeah, I didn't see it either. I don't want to do that. No. Okay, let's do this here. 1, 2, 3. There we go. Compare your estimates in parts A and B with the exact values. So can you do them now? Can you do it exactly?
Yes.
Yeah? Okay. How are we feeling about this? Decent? Okay, put everything away.
Nice.
Woo! We're starting here with some sort of generalized surface that's continuous. Generalized surface that's continuous. And what's going on as you move to the right here? What's going on? You're zooming in. There we go. We're zooming in. So the idea is, as you zoom in, what does it look like? What's going on?
It's getting locally linear.
It's getting locally linear. Oh, look at that. It's getting locally linear. Oh, we're going to talk about tangent planes. That's right. So the idea is these are the what diagrams of these three situations. These are the contour diagrams of those three situations. So as this goes to, this view goes to here, and then this one goes to here. And what do you end up with? You end up with something that looks more and more like a plane. How can you look at a contour diagram and tell if it's a plane or not, or what's the thing that tells you it's a plane?
Line. Straight line. Or
Any straight line, any straight line you cut, and specifically we weren't looking at straight lines like that when we were looking at planes. We were looking at straight lines that were parallel to the x and y axis. But any straight line you cut, what do you see when you're traveling on those paths? Yeah, the same what? The same slope. Any linear path will have a constant slope. It's going to be different every direction you go in, except if it's parallel, I guess. But the idea is any cut you make. Yes.
And that's like super zoom in.
Correct.
Just like you do with locally linear.
Absolutely, it's exactly like we do. So this is one of those cases where when we apply linearization to 3 dimensions with the same techniques that we applied to 2 dimensions, nothing really changes except the nomenclature. It just gets pretty visually impressive in terms of the the conventions we have to use to describe what we're doing, but it's not actually that terrible. That being said, we need to make sure we understand what each piece means, because it's really, really easy to get lost in the labeling. I had several ways to write the equation of a plane. What was the first way we had for writing the equation of a plane? Do you remember what that formula was we wrote it? Do you remember how we did it? It's in chapter 12. No, that was not chapter 12. That was chapter 13, because for ax plus by plus cz equals 0, or equals d, we need the normal vector, right?
Yeah.
Before we had the normal vector, do you remember what the equation of the plane was? It was z equals what? Z, no. Do you remember this?
Oh, z naught.
Z naught plus what?
Yeah.
Remember m and n? Remember this?
Yes.
X plus y.
Do you remember this?
Yeah.
Y minus y naught, right? And what was n? Change in y direction, right? And this was change in x direction, right? Well, that was back in chapter 12. That was before normal vectors. That was before cross products, right? And we found that numerically you'd have like a table of values. But now, what do we now have? This is what? Change in the x direction is what? Fx. And change in the y direction is Fy. Exactly. Right. So what do we now have? We now have an algebraically defined way to find the tangent plane to a surface. Because what do we have? Well, if you have a point, well, here it is. You have a point AB. A is going to be the x value, and B is going to be the y value. And then f of AB is you have the z value, you have your x naught. I'm just bringing this back to the notation we were using before. But now do we have a way of algebraically finding this and this? Absolutely. So now do we have a really straightforward way of finding a tangent plane? Yeah, we absolutely do. Now here's where it gets fun. Calculating tangent planes, not the hardest thing in the world. Using the information you get from them can be a little hard because it involves some relatively deep 3D pictures that you kind of just have to have a snapshot in your head of. There's one really, really important picture from this section. So this is, this is the presage. So this is the first picture, I guess. So the idea is you have this plane that is tangent at that point. This is what we're looking at right here. And the right click is the setting, just to be finicky. Not sure why. But the picture that I really want us to look at is this one. Well, I'll put this in first, I guess. No, let's just go straight to the picture. This is better. Woo! All right. Let's do this. It's a good time. And I'll pause. So what are we looking at? You have your point AB right here. And then at this point right here, this is where the tangent plane is the only place it's touching. Tangent, touching in Latin, right? Whatever. So the idea is this plane that you're seeing right here is a part of the tangent plane. That is straight above this box. If you've measured a delta x and a delta y in direction from it. So here's the actual surface right here. Here's the actual surface. Sorry. Here's the actual surface, and this is the actual tangent plane. So I kind of ask you the end question here. What's the point? Like, what's one of the points of using tangent planes?
Estimation.
To estimate, right. Sometimes surfaces are going to be written with formulas that are going to be very, very nasty. Generally speaking, when you find a tangent plane, You've simplified it, made it easier to work with. For values around here, for values around that point of tangency, the tangent plane is relatively close to the actual function values. This is not, I'm not changing anything about the laws of two-dimensional calculus. The challenge is understanding what all these symbols mean. So you have to kind of be very careful about this. So the idea is, if you have AB and you go to, you fix, usually this is fixed. If you go to a point XY, the change in X is, well, how do you notarize that? You notarize it as delta X. The change in Y you notarize as delta Y. So if you travel that distance, you end up at XY. So what you're going to do is, one thing we're going to do is, let's say we're having a very hard time estimating this value right here, the actual function value. You can find the tangent plane and then find this point right here. That point right there. You've done this before, but you've done it in two dimensions. Like if I cut this plane right here at that angle, this would be identical to questions you've done before. We're just adding in another dimension. So here's the deal. You're going to center around usually finding this value right here. Take a look at this value right here. This is the important one that we're going to look at right here, because that represents the distance from, like, what point is this right there? That point is, what's the z value there of this point? Have we gone up or down or neither when we've traveled from that point to that point? Neither. You've not. It's stayed the same, right? So if you have your initial z value and you know this value right here that I've circled, you can find this estimate. But what are the elements of this little piece? You need the partial with respect to x at AB times delta x, and you need the partial with respect to y times delta y. You need all of those things. It's rather important. So let me pause for one second. If you could have discontinuous velocity, what would that mean?
That means you change your velocity.
Yes, it would mean can you instantaneously change velocity? No, you can change velocity very, very quickly, right? But what would be possible? Take this to like the ad infinitum. Is that the proper phrase? Like take this to the extreme, right?
Yeah.
Is it ad infinitum? Ad infinity? There's a Latin phrase.
Ad absurdum.
Ad absurdity.
Yeah.
Is it ad absurdum?
Tom.
Ad absurdum, right? Thank you. I would actually like to. I gotta look that up. So I don't actually. It's this is called undermining yourself when you try to sound smart and use a Latin phrase, but it's wrong. Nice. If you take it to the extreme, if you could have discontinuous velocity, what would that mean you could do? Yes.
Teleport.
You could teleport. So I would get these trampoline velocity graphs where it would be like you'd have a negative velocity and then all of a sudden it would jump straight up and I'd be like, sweet. It's like that movie, whatever, with the guy and he could teleport, like thinks real hard, and all of a sudden he's on Mount Everest and shivering.